Okay, so good morning to everyone, and thanks for coming. I'm pleased to introduce you, Richter, who is visiting to us from the University of California, Davis. He's the PI of the Exos spectrograph, which is a spectrograph with a high spectral resolution of between 30 and 3 meters per second, more or less, and covers the range from 5 to 28 microns. This spectrograph is mounted on SOFIA observatory. Additionally, he is also the co-I of the spectrograph Texas that is mounted on the RTF. Well, today he will give us his talk entitled High Resolution Thermal Infrared Spectroscopy in the Age of Jwst.
All right. Thank you very much for having me. This is my first in-person talk since, over 2 years ago. So I'm excited by that. It's also my first hybrid talk. I didn't do any teaching. I'm not on the teaching faculty at Davis. So my apologies to those online if this doesn't work. Just never sure about this. As Pablo said, I'm going to be talking about high resolution thermal infrared spectroscopy. Mostly I'm concentrating on 5 microns and longer. And it's going to unashamedly be focused on the work that I've been doing or that people have been doing with my instruments, with the instruments I'm involved with. Here you can see the Exos grating. So that is what makes high resolution possible. It's a literally 1 meter long bar of aluminum that has been diamond machined to provide reflecting facets, which you can see here. The light comes in at nearly grazing incidence. It's an R10 for the spectroscopists among us, the diffraction grating people among us. And lightweighted, it weighs about 15 kilograms. So that puts it into perspective what lightweighting of aluminum can do for you. It's still pretty heavy. I do want to mention the collaborators, particularly John Lacey, who's been my mentor since about 1993 or so. I've worked with John very closely in building first Texas, then Exos. And Curtis DeWitt has been really, indispensable in terms of working with SOFIA and Exos. He's been with that project for almost a decade, or actually, I think a little bit more. Okay. So, come on. Are you going to work? No. So let's just do it the old-fashioned way. Just to bring everybody up to speed, I'm not sure how many of you are thermal infrared astronomers. Some of the basic backgrounds. And one thing, of course, is that the background from the telescope and your window and the sky dominates the signal over almost all of the wavelength. You can see here just a plot from Alan Tokunaga's chapter in the Astrophysical Quantities book. So here's a ground-based telescope. This is a photon flux. And when you're in 10 microns, you're more than 5 orders of magnitude above what would otherwise be your background if you were, say, a JWST in a cold space telescope. So, which would be the zodiacal emission. So when I first got in, I remember someone saying, doing mid-infrared astronomy from the ground is kind of like observing during the day with your telescope on fire, because there's light coming from everywhere and it changes. So another thing that I want to make sure everybody's aware of is the Earth's atmosphere really severely impacts where we can observe. And so it's just these windows in the infrared, JHK, or well known from near infrared, then you get into the thermal and it's L, M, N, and Q band out at 20 microns. Very few people observe it in Q band. Come on. Not that. There we go. Another thing important to the mid-infrared, there are really a lot of features. This is an area where you can see solids like dust, where you can see ices, you can see large molecules. For all those, you want low resolution is fine. And so your instrument only needs to have, something, well, even in filters on a camera can work for those features. As you're starting to study atomic and ionic lines from, say, H2 regions, shocks, or galaxies, then you end up wanting higher spectral resolution, say up to or down to about 10 kilometers a second. You might want for a shock, for example. But in many cases, 100 kilometers per second is fine. But if you go for the molecular lines, and especially if you're studying quiescent gas, then you want the highest resolution. So sort of 1 to 20 kilometers per second. Not many things do you really need 1, but I'll be honest. I think probably 5 is fine for most things that we've seen. But the molecular lines, the advantages are you're getting rotation and row vibration transitions. The row vibration is especially important because in a single setting, you can sample a wide range of excitation energies. And so you can really use that single observation as a diagnostic of what's going on in the gas in terms of temperature and density and optical depth. Often we're observing gas that's in absorption against some bright continuum. Not always, but that's frequently the case. And another big advantage for the mid-infrared and these rotation vibration transitions is we can see molecules that don't have a dipole moment, so that they're unavailable with instruments like OMA or EROM or the interferometers in the millimeter, submillimeter. So molecular hydrogen, okay, those are pure rotation in our wavelength range, but methane, CO2, those are things that we've found useful to do in the mid-infrared. And yeah, a little bit of history. This is going back to early observation with John Lacey's Herschel instrument, which in around 1990 was really a state-of-the-art instrument. First discovery of interstellar acetylene. Right here you can see it. And first discovery of interstellar methane. Sorry, actually here. Those are not great spectra, let's be honest. I applaud John for getting that, but this is something you'll see the improvement over time. I'm gonna pretty much skip this, I think, just to orient you, though there are some near-infrared spectrographs, and then these are more the mid-infrared. These are the 3 to 5 microns, high resolution in all cases. But I do want to point out there are the space infrared spectrographs, because there you are colder telescope, sensitivities improve, you're up above the problems of the atmosphere. So first came ISO SWS with a resolving power of about 2000. There was a Fabry-Perot mode as well, but not much came out of the Fabry-Perot to my knowledge. Spitzer IRS, their high resolution was RO600, so that's about 500 kilometers a second. So, but then JWST MIRI, which we're all anticipating and will be fantastic, has a resolving power of about 100 kilometers per second. And I'll bring that up over and over during my talk. To give you an example of what you can do with these different resolving powers, Here's a simple model of absorption in HCN and acetylene. And all of these spectra in the model are signal to noise of 100 for each instrument. And this would be Spitzer. This is JWST. I called out that the depth of the acetylene Q branch is about 20% deep. Here was Urschel, and oh, goodness gracious. It suddenly worked all at once. I think it likes to go back, not forward. Well, actually it went forward. So. And then here is R of 100,000, 3 kilometers a second, which is Texes and Xes. And then, right, I also want to point out, this is a typical wavelength coverage with our Xes instrument. So when you do the high dispersion, just because your detector real estate is limited, you end up with a limited amount of wavelength coverage. We do have another mode, which actually can cover 40 inverse centimeters at one shot, which Pablo has been using some. So that's something we really like about Xes. Hey, it did work. Now, if you remember that 20% the JWST model, here is what it is if you blow up the coverage of the Q branch in with at a R of 100,000. And you can see that now it's going almost 40% deep. So the higher the resolution, the increased sensitivity you have to narrow lines. It's not something that's surprising, but this really graphically shows you exactly what I'm talking about. The other thing I want to point out is here you can start to see the odd even effect in acetylene. That's because this is an optically thin model. You end up having a difference in statistical weights that shows up in the absorption for the molecule. And one more thing, down here you see the R of 3000 resolution element, which would definitely start blending some of these lines. So JWST will see acetylene all sorts of places, but it won't be able to get the line profile at all, at least in most of the nearby objects. Okay, just to remind you though, this is that same acetylene spectrum, and then here is atmospheric transmission from Mauna Kea in red and from SOFIA in blue. So yes, we can have really nice high resolution, but we still have to deal with the atmosphere. JWST will not, and they will really enjoy that. We all will really enjoy that. A little more history. This was state of the art for high resolving power. So this is something like 50,000, so 15 kilometers a second. And back in 1986, it was a Fourier transform spectrograph at the Kitt Peak 4 meter. And they had a bandpass filter to cut down outside noise. So out here is outside the bandpass. That's the pure noise of the observation, just to orient you. This was a long integration, 6.5 hours on alpha tau, 4 hours on alpha Ori. Very, very bright sources. So this is what we were limited to in 86. Here is alpha tau from the IRTF with Texes. So a smaller telescope, better sight, larger wave resolving power, larger wavelength coverage. And the big one is this was 4 minutes of integration. All of these features are real. You can take a sunspot spectrum, line them up, you will see almost all these things are water lines that are in the surface of alpha. So this was really fun. We really enjoyed this when we got the spectrum and saw what the instrument could do. This is way back in 2000. Yeah, okay. Now, going on to some science, I'm going to focus first on observations of water in young stars. Now, observing water is difficult because of water in our atmosphere. There are certain lines that you can do either at 3 microns that, with PriRes, for example, and you can do, there are some at 12 microns. And then of course you can do them in space. So this was Spitzer IRS and observing a T Tauri star, and the unmarked lines are all water coming from the disk around this young star. So it's warm water and it's emitting from the disk. Most of these stars are too faint to do from the 3 meter, unfortunately. So it's not something that we pursue. It's actually, well, I'm going to point out this is 2008. In 2006, we got to take Texas to Gemini 8 meter. And just this is the Texas instrument. For reference, that's me hunched over the computer laptop trying to make sure we could talk to the instrument as we were installing it. So we were at Gemini, and the sensitivity goes as d squared for just the raw sensitivity, and which is 7 times better than IRTF. And so we started looking at a T Tauri star, RWRIB, but we were looking for HCN emission, not for water, because water is hard to get through our atmosphere. We didn't think we'd be able to see it. As we were doing it, we're reducing the data. We reduced, first file, pipeline, reduce it right away, copy the second file, route 2, better signal to noise. Then we wait a bit. And one of the collaborators was on the data reduction, and he was saying, I'm not seeing HCN, but I think we want to keep going. There's some line coming in. And eventually we realized it was water, and we got this spectrum off RWRIB. And it looks double profile, double humped, especially if you have the model line to guide your eye. So water emission coming from 0.3 to 1.1 AU. And one of the advantages of this wavelength and these sorts of transitions is that you are in that, as far as humans are concerned, more interesting range of radii from the star. The near infrared 3 micron water lines are really coming from much closer in to the host star. The other thing I want to point out, this is JWST's resolution element. So 100 kilometers a second means that line profile would be invisible. It would not be able to model it and look at the emission. So, mind you, the signal to noise will be much better. This is showing some of the lines that we do for water. They're all very narrow and very weak in our atmosphere. They are higher lying lines than what is in our atmosphere, and that's why they're able to come through. This is just a model from Mauna Kea of the atmosphere. So once we observed and found we could do water in one star, the next step when we went back to Gemini was to look at a bunch more stars. And this is from Colette Salik's paper in 2019. This is one single Texas setting for a variety of stars. You probably can't read them, but DR tau, FC tau, HL tau. And overall, Colette was able to derive the excitation temperature and a radius out to about 1 AU. You can see these line profiles are not uniformly the same. There are differences. So different stars have different features. We still need to understand exactly what's going on. And the other thing that I want to point out, the faintest source, which actually I think I cut off from this graph just to make it fit. was at 0.6 Janskys, which means that there are a lot of stars that we can do when we're on Gemini. I guess I didn't mention it earlier, but Texies is always open for collaborations. So if you have any idea about what you might want to do, definitely let me know later on, because sometimes it's a problem getting enough successful proposals on Gemini to really make it worthwhile. Okay. Then going on, Nagita in 2018, she published a paper where we were looking not just at water, but also at the organic molecules, HCN and acetylene. And you can see over here on the left, a plot comparing HCN in black with this. Why does it do that? Come on. Okay. HCN in black, acetylene in blue, and then over here the three organics in black and the one water line in blue. And what you can see there, if you look at the line profiles, they are essentially identical. This means that kinematically, at least, you would imagine the gas that's doing the emission is at the same location in the disk. It's unlikely to be in widely different locations. So now, if you can't resolve with JWST, but you have really good signal to noise, you can look at line fluxes for these different molecules and know that, yes, you're comparing apples to apples in terms of locations in the disk. Without this spectrum, you could always ask, but are they in the same place? And no one would really know. Okay. Now I'm going to go on to SOFIA, and feel free to ask me about SOFIA in the question period. I'll plant one there. I'll be happy to talk about it as best I know. So SOFIA is a NASA DLR collaboration. It's a 747 airplane with a telescope in the back. The effective aperture is 2.5 meters, and it fits within the fuselage of a plane. That's something that's always a little amazing to me. We fly at, I think it's around 12 to 14 kilometers, 39 to 43,000 feet. I haven't done that conversion. And we usually look at an object for between 30 minutes to 4 hours. And that's a restriction just because when you take off, you've got a limited time, you've got to get back. And you want to try and maximize your observing time. You can't really see it too well in these pictures, I'm afraid, but it is a shirt sleeve environment. The telescope's in the back, that's our instrument there. The investigators are sitting here, telescope operators are over there. And, okay. When we proposed for Exos on SOFIA, we knew that this wavelength region, 5 to 8 microns, would be very important. That's where water has a strong vibrational band, makes it almost impossible to observe these frequencies from the ground or these wavelengths. Also, methane is here. That's also very important, a very nice molecule to be able to study. This is comparing SOFIA in red and Mauna Kea in blue. And then if you zoom in, you can see that even where it's really hashed up, there are a lot of points, there are gaps. And with enough of a Doppler shift, say only about 20 kilometers a second, you can observe these lines because they're Doppler shifted off the telluric residuals. Okay. On our very first flight with Exos in 2014, we were able to look at a massive star that is surrounded by gas and dust, although that was the idea then. Now it's looking more and more like it probably has a disk that's around it. And we detected, well, in black here is the spectrum of the object, AFGL 2591. In gray is a spectrum of Vega, so a hot star for comparison of what the atmosphere is doing. And then this is the division. And we found 10 water lines in this single observation, including right here is absorption out of the ground ortho state for water. I think it's ortho. And then also 118 or H218O. I should correct that. So we were able to get the line widths and looking at the excitation temperature and column density from this single observation. And and I should say that was from Nick Indriolo back in 2015, I believe. In a more recent paper, Nick Indriolo et al. 2020, he took observations of another one of these types of sources, FGL 2136, and he combined cryres data at 3 microns, Exes data at 5 to 7, and Texes data at 12. And this is the sum of the Exes spectra. Again, H18O is in red, and the 6.113, it's got to be somewhere in here is the no, over here is the ground state absorption. But having all these lines, Nick was able to show that the analysis tool we had been using forever, back John Lacey's 1989, 1991 papers, where you assume a background lamp and a slab of gas in between does not make sense. Intuitively, we wouldn't expect it anyway, right? You expect there to be gas and dust mixed, and so a real radiative transfer approach is necessary. And Nick started doing that. And the other thing he did that was interesting, you can fit these lines with a pair of Gaussians. So these are a couple of Exes lines, and this is a cryres line. And the two Gaussians have essentially a common central velocity. Now, recent ALMA continuum observations found a disk around this object. And what's also interesting, I don't have it here, but there's a line map that shows that the velocities are indicating the disk is rotating. And so that's really why we're confident it's a disk. So one of these features is basically coincident with the midline of that disk. And the other one is more corresponds to what the velocity we'd assume for one of those density enhancements. So we're starting to use our observations to get an idea of the gas motions in the disk around this object. Finally, I'll point out, or I'll remind you, JWST's radial velocity or velocity resolution is 100 kilometers a second. So these lines would all just be invisible. The line profile would not be there. Okay. Going to change gears and talk a little bit about evolved stars. And this is work that Pablo has really been leading in a very important way. Mostly with Exes is what I'll be talking about. And the first thing I want to say how evolved stars are wonderful targets in the mid-infrared. They're really bright. They have lots of molecules in their winds. And because they have winds, there's interesting dynamics. And so you like to have the spectral resolution. So I'm very happy that we've fostered this collaboration, because otherwise, before Pablo and Pepe started working with us, we didn't have anyone who was doing evolved stars. Okay, this is a recent paper. Yeah, just came out recently, 2022. We're looking at molecular hydrogen towards IRC 10216 and actually seeing absorption in one of the molecular hydrogen lines. And this is an idea that's old. If you look back at old Fourier transform spectrograph papers by Gigi and Ridgway, they were looking for this and they could not find it. And it's really gratifying that we found it. I'm going to point out these, it's normalized to 1. Here's 1%, and here's plus and minus. So this is a very high signal to noise spectrum. As well, it's IRC plus 10216. It's the brightest object in the sky after, I think, the sun, the moon, and Venus at these wavelengths. So, but the important thing here is that from this absorption, we're able to determine a mass loss rate that's independent of the CO to H2 ratio. This is directly looking at the bulk of the material coming off the star, and that's what's new. Going on, another molecule that I'm very happy we've only recently been able to do with Exos, it's CO2. And CO2 is well mixed in our atmosphere, and it's got very strong bands. And so even from SOFIA, the main band at 15 microns, 15.5 microns is unobservable. But there are some satellite bands, some high excitation bands that in this star, our Leo, Pablo is able to identify. They came out Doppler shifted from what was left in our atmosphere. And so we're able to study it. And so that's a program now that you've got with Ed Montiel, a postdoc at SOFIA, who is, or no longer a postdoc, a scientist at SOFIA, where you're looking at CO2 in a wide variety of sources, including going on to later evolutionary states. So looking forward to doing those observations. Okay, comparing again back to JWST. I've already emphasized the need for high spectral resolution, but I want to make sure you understand how much better the sensitivity is going to be with JWST. So TEXI's on an 8 meter, the continuum sensitivity with JWST is thousands of times better. It's just the data we're going to get from JWST is going to be amazing. It's going to be very exciting and change the field, I'm sure. For unresolved lines, well, the high resolution does better. Now we're only talking about 50 to 100 times better with JWST. So if you only care about detecting line fluxes, again, JWST is probably the best way to go. And the reason why is just as I was saying earlier, ground-based telescope has so much background, where a cold space telescope, your sensitivity, you're not fighting the background at all. It'll be a little better when we get the ELTs, because as we get up to a much larger mirror, then we'll again have that gain in sensitivity. And so they are planned. Each of the ELTs has a plan for an instrument at high resolution, at least for 3 to 5. That is, we'll be doing 3 to 5 at R of 100,000. What's fascinating there is it'll be an IFU. And so you'll be able to, as you exploit the spatial resolution of the large aperture, you'll be able to start resolving and getting spectra for each point. So that'll be fantastic. GMT nears on GMT will be a little lower spectral resolution, give you 3 to 5. What's amazing for this instrument, in my mind, is you get all those infrared bands in a single observation. So it's kind of like X shooter on VLT, move to longer wavelengths and doing it all at one time. These two instruments, I'm going to point out, use immersion gratings. They're not using a meter-long grating to get their high spectral resolution. They're using a silicon crystal that's been etched to give grooves. TMT Michi, which I'm a part of, will have R of about 100,000, at least to the acetylene Q branch, where the atmosphere starts dying out. Comparing this instrument with JWST, well, Continuum, still hundreds of times better. JWST will be hundreds of times better. But when we're getting towards unresolved lines, it's only a factor of few. The problem is that truly an unresolved line is difficult to find. So in practice, it won't be quite that good. But it is close enough that the ELTs will be observing the same targets as JWST in some cases, and not getting the same signal to noise, but getting enough that you can really decide on the line shapes and start studying the kinematics. Another thing that interests me about TMT is there are plans to observe in the morning hours. So twilight, even after the sun comes up. Having an infrared AO system will enable us to observe during this time, and it'll only be good for the mid-infrared, really. So this is a way to use telescope time, and we'll be able to do some very significant surveys, in my mind. Okay. How am I doing on time? Okay. So now I'm going to end with talking about how do we combine the sensitivity of JWST with the high spectral resolution? Because really, that is what I would most like. I would love to have a high spectral resolution cold space telescope. And the problem is we need to go from the grating that's this big and weighs 15 kilograms to something, well, something like this would be nice. It's about this big, and I actually don't know what it weighs. It's an immersion grating. It's made out of germanium. The basic theory for gratings is the resolving power is the optical path difference, where I'm assuming it may be in transmission. So it's just the distance from the nearest groove to the farthest groove, divided by the wavelength. And you also have a factor of 2 if you're going to be a reflection grating. And that's why we have that really large grating. We're at 10 microns. So that's a million, it's a 1 meter grating. That's a million. We'd use it in reflection. So we have a theoretical resolving power of 200,000. We don't get there. It's hard to get to the theoretical perfection. So this grating made of germanium has a 19 millimeter aperture or beam size. And it will deliver R of 40K at 5 microns. So we're relaxing a bit the spectral resolution, but we're really going to be able to lower the mass. We've shrunk the mirrors that feed it by a factor of 16 because germanium has this N equals 4. The index is so high, it shrinks the effective wavelength of the light within the crystal. And so the resolving power, if we shrink that, we've driven up the resolving power. Okay, another nice thing, 2 to 18 micron transmission for germanium. And there are now detectors that work out to 14 micron that don't need cryogenic cooling in space. They can be passively cooled. JWST is passively cooled to this sort of temperature. Some of their detectors do not need any cryogenic cooling. Okay, so thinking about this, where would we want an instrument, what would we want to emphasize? I would argue that we want a wavelength range that has lots of features and can't be done well from the ground. And so I'm actually looking at something from about 3 microns to about 8 microns. And that way we can put that in space. We avoid the interference of all this atmospheric water and CO2. And it's nice because there are a lot of molecules of interest there, like we were talking about. Also at these wavelengths, we would benefit from the cold telescope. If you go to very short near infrared wavelengths, you don't benefit so much. And if you go to very long, Herschel benefited some, but if you were to try and put a much longer wavelength telescope in space, you wouldn't get as much benefit from being cold. So, as always, there's a trade-off between the wavelength coverage. So this is 8 microns to 5 microns. This is an Exos survey we've done for some of these objects like AFGL 2591. And here was one of our spectra. This is actually when you look at it on the detector. You can see that this is a small region. We had to stitch together about 13 of these observations, each one taking 50 minutes to an hour to get good signal to noise in order to cover the whole range. I would argue that we want our first high resolution space spectrograph to be optimized for point sources and large wavelength coverage. We can't do both. We can't have a long slit and a large wavelength coverage. So I think we'd go for optimizing point sources. So we're working on that. We call it Gigi, the Germanium immersion grating instrument. And it's that one germanium immersion grating. In the design, we could get our 40,000 from 3 to 5 and 25,000 to 5 to 8. What I really like about this is by having a dichroic that splits the light into 2 arms, we're able to cover that entire wavelength region in one shot with no moving parts. And that, to me, the idea of no moving parts in space really is a big selling point. As I say, we're optimized for point sources, and I think that this would be really exciting if we have enough sensitivity to start characterizing exoplanet atmospheres. Looking for all those features that are important in our atmosphere, it would be really nice to know how much water there is in exoplanets. I haven't done all the modeling, and I haven't done all the work to decide what size telescope we need. Right now, we're at a point where, if I can actually go back, we're still studying this in the lab to make sure that the germanium is giving a good spectral profile. And so we're feeding it in with a laser light, and then we're looking and seeing what comes out. We were really close, and then COVID hit. We also had problems with detector and electronics, which has been hard to deal with, but I'm hopeful that once we get back in the lab, we'll be able to continue work. And so summary, high resolution mid-infrared or thermal infrared, great to study molecular features. We'll be looking at some targets that Jwst will right now, but once the ELTs are around, that'll be much better. And I really hope we get an infrared spectrograph, high resolution in space. We really haven't had one. And so I think there's a lot of science that we're missing right now. And Gigi is one option. And just for fun, the picture of me through Exos using our pupil mode. We can image a little bit too. Thank you. That's it.
Thank you, Matt. So, do you have any questions? Go ahead.
view of what can be done with high spectral resolution. Concerning this future space, what kind of telescope do you want to have?
I'm greedy, as big as possible. Exactly. You knew the answer. So I think that to me, it makes sense to try and get this as sort of like one of the smaller missions. If we can show NASA that with, say, a 30-centimeter telescope, sort of a Spitzer size, that we can really characterize the exoplanet atmosphere, then I think that that might be attractive. There are other options, of course. The germanium immersion gratings have only been available, well, I think since around 2015 is when I saw the press release describing this. They are being looked at for instance, Michi, our ground-based instrument. But I think that one of the next generation, very large missions, it might be possible to include something like a Gigi in such a flagship mission. Personally, though, I'm still going to look at how small a telescope we can do. 30 centimeters, 1 meter. I think 1 meter would be plenty. Yeah. And well, the thing is, remember that this is a point source optimized. And so we would match the slit size to whatever it is giving us. We're not going to try and resolve nearby features. We're going to look at one target, the planet plus star system, and then try and tease out the atmosphere by correlating on the Doppler shift signal. That's the way we have to do it. And you're starting to see some of that even from the ground. Well, it's been going on with PRIRES for, I think, maybe 6-7 years. And being able to get that large wavelength range, being able to get the higher signal to noise, we would be able to use so many more lines, because of course you would end up stacking the lines or doing a cross correlation of the models to get to the best answer that you can, get the most that you can out of it. Any other questions?
I have a comment.
Oh, yeah.
Before my colleagues. I see that you are doing a pioneering work in the infrared, but there is something when you compare with other wavelengths, and with telescopes, you have pipelines that produce you data that are practically ready to be used. I have been working with Pablo and with you about the start, and it's extremely hard to work with the infrared data. It's not so easy.
Yes.
And this is something that maybe if you want to create a community around the high spectral resolution with infrared, the interest for young people will see high spectral resolution infrared. That's my work. Talking with people working in this field is extremely hard. How we can do to convince the community that it is absolutely necessary to have this kind of instruments, because you are offering to the community the possibility to detect molecules like acetylene, like methane, like diatomic acid, all these molecules that lack of permanent dipole. This is crucial for astrochemistry.
Yes.
However, you see the community of astrochemistry, all the young people,
ALMA is a wonderful instrument, right? It's changed the sensitivity and what's possible in enormous ways. So it makes sense to me that young people would want to gravitate to that. So getting a community is hard. And my usual joke about So mid-infrared observing, mid-infrared imaging, all sorts of spectra. That's a small community or a niche community in some regard. JWST will change that, hopefully. And the high resolution, high spectral resolution mid-infrared community, that's beyond niche. That's getting to a cult. We are very small. There are, I can probably name most of the people who do it. And that is because it is hard. It would be easier if our pipeline worked better, but we have a small group. And so I'm impressed with Texies that John Lacey has gotten the pipeline to the level he has. We don't have the manpower, which is another reason why we'd want a community. I tried to build a community with Exes before our first flights, getting some of my colleagues that I knew would be interested and talking about, okay, what science are we going to be doing? What would you be interested in? And we'll need you to look at the data. And it was that last bit, that really pouring in that didn't happen so much. I couldn't offer anything more than the excitement of new data from SOFIA and Exos, and everybody's busy. So I think it might take to really build it is getting something like this instrument or funded by NASA, because then NASA would make sure there's a really effective pipeline. JWST will help because there will be people who, they've looked and they said, oh, I wish I knew what the line profiles were. But some of them will be disappointed that from a ground-based telescope, you just can't see that object. We'll see. The other thing to bring up, right, it's the mid-infrared. There are not many instruments alive right now. There are fewer now than there were in 2010 in terms of mid-infrared instruments on ground-based telescopes, because the argument from the telescopes is the proposal pressure isn't there. The community doesn't want it. You can question about whether it's a chicken or egg program or problem in terms of if the observatory promoted it enough, the community might be there. We have managed to keep Texies going on the IRTF for 22 years, which for a visitor instrument is fairly impressive. And we still have probably about 3 or 4 runs per year on the IRTF. Most of that is solar system. There is a community there. As I said earlier, Gemini, I would like to get back there to the 8 meter where the sensitivity is better. So sometimes we have trouble getting enough proposals that are good and are accepted to merit a run. So yeah, and look for a proposal call from Gemini probably in October that will be planning to be back on the telescope in 2023A. That's my hope. And if you have any ideas how to promote a community, please tell me. Let me know.
Question? Yeah. You mentioned about exoplanet atmospheres not living in this space telescope, but from ground, are you aware if someone has tried to observe an exoplanet?
So in the thermal infrared, yes. In the longer wavelengths like the N band, 8 to 13 microns, no, because the sensitivity isn't there with even 8 meter telescopes.
Yeah.
But in the 3 to 5, it certainly has been, the people have been doing it, looking for lines like, or species like CO and H2O. And I think it's shorter wavelength methane as well, particularly in absorption. I might be confusing it with like a HST. I know HST has done it.
Yeah.
I think maybe. Again, usually the process with like Cryros is you observe a region, you're observing star plus planet, even with Cryros AO feed, you're not separating them. And you get the spectra and you Doppler phase them to the planet. And then you do a correlation with a model for what the exoplanet atmosphere is. And you're able to get to a few sigma significance that, yes, there is CO in this planet atmosphere, for example. JWST will do wonderful stuff, just looking for where the lines are close together. And so being looking there, and especially looking in transit. So looking for where the atmosphere is absorbing from the host star.
Okay, I have one question for you. How do you control in SOFIA the position of the telescope to prevent losing the object you are observing?
So yeah, this is something that in the airplane environment, we've all flown, we know what turbulence is like. SOFIA's telescope is gyroscopically controlled, and then there are large magnets that are applied to try and keep it pointed. Actually, if this works, and I hope it will, I have a way of showing. Okay. That. And good. So this is a movie. It's only about 40 seconds long. You can see the telescope. Oh, I've sped it up by a factor of 8, because otherwise it would be too much. You can see the telescope is just sort of wobbling around a little bit. But over here, you can see the Jupiter and its moons, and they're rock solid in that screen. Because of course, the telescope isn't wandering around, the airplane is wandering around the telescope. And so it's always a little bit amazing to me when we encounter turbulence, we're watching the telescope dance, knowing that it's actually within, to better than, certainly it seems better than a half arc second is in terms of its stability on source. So it's amazing. So SOFIA is a fun instrument, fun observatory. It's a little maddening at times as well, but the technology that's involved is really amazing. Sorry.
I'm not sure you can make a comparison, but how much observing time do you get from SOFIA as compared to a ground-based telescope?
So this is one of the arguments against SOFIA. No, it's fine. This is definitely foremost in my mind because I'm observing starting next Monday on SOFIA. I return to Southern California. And at least as I understand it, those 2 weeks will be the last 2 weeks that I get to observe on SOFIA, because the project's being wound down and Exos will be one of the first instruments to be wound down. I don't agree with it. I'm screaming a little bit to people who I can, but we'll see. One of the reasons why NASA is going to cancel SOFIA is it's around $80 million US per year. And each flight, we get only about 8 hours of observing time, as opposed to, ground-based telescope, optical infrared, you can assume 10 to 12 hours. And the longer wavelengths, millimeter, sub-millimeter, you're observing 24/7. So the other thing about SOFIA is that in a good week, it flies 4 times. And so not only are we getting a small amount per night, but we're not having that many nights per year. and it's expensive. My only reply to that can be, what price do you put on completely unique data? And that's a question that every scientist has to answer. And, you know, people can argue that, well, you know, with that money, we could build a new survey, infrared survey satellite. Yes, there have been a couple of those. Are you going to get something new? But, right, that's SOFIA right now is on the chopping block, and it looks like it's definitely going to go down. But we're going to keep working. We're going to try and get the best data we can in the next 2 weeks and encourage our colleagues to publish them really quickly.
It's kind of like to develop a new instrument like the telescope you were proposing with Gigi.
Oh,
That would be
yeah, it'll be a long time.
tens of years, or I don't know.
Well, to really get it in space, it would be I would imagine, yeah, you're right. 15 years, maybe 10 years. Probably not my career. Who knows? The first step, we still have to finish the lab. And I want to verify that it works warm and cold with a laser. Because to me, it would be irresponsible to really make firm plans going beyond that. That being said, I'm a soft money researcher. I need my funding. And so I do have a proposal in, assuming we're going to be able to do it right, to build a ground-based prototype. We have a cryostat already. We have the design that I showed you. And we know that we could go to Lick Observatory, which is not a good thermal infrared site, but it is a 3-meter telescope. And if we can get honest to goodness data showing that the 3 to 5 micron arm works, then I would feel much better going to NASA and saying, now we need to get this. Well, in space is where it needs to go. A balloon wouldn't be bad. There are also balloon programs that might be of interest, but then you're not getting the cold telescope. Your sensitivity really doesn't improve. So, in my mind, that's the process.
Thank you.
I have a question for Sabine. I think that the 8-inch high spectral resolution was achieved at the same time that high angular resolution using the photometric. I think it was 2 telescopes. It was the group of
Towns, yes.
Why this kind of observation that we say there is not too much output from these instruments? However, I remember some results that was very, very, very spectacular. I was limited to very high source height.
Yep.
But it's something that we produce a lot of physical information, because now when you are sharing the mid infrared with angular resolution of 1 second, microfiles, and you have to model the source. That means that you are depending on the quality of the model.
Right.
Having high angular resolution at the same time that high spectral resolution is probably something that, from the scientific point of view, would be really very interesting.
Yes.
And keeping in your space project, why not 230 centimeter small telescope doing the observatory?
So that would definitely not be my project. That would be getting too complicated for me. And so I can see the point that it would be really nice to have these two, well, light buckets that you feed to a common, but interfering them. So you need to have some reference frequency in order that you can phase them up properly. And the people are still working on the high spatial resolution. Yeah, you've got VLTs doing some marvelous work. Oh, I forget, the gravity, I think, is one of the new instruments that they have for their interferometer. And it's working at these wavelengths. So it is hard. I have talked to people who have been up at the Keck telescope trying to make the Keck interferometer work while I've been observing on other telescopes. And it is just really hard. And maybe, well, I mean, there are Nobel Prizes in it for sure, as we've seen recently, but I think it would be better to get further, a bigger community on the ground. And yeah, actually, I can imagine the EELT with the IFU in 3 to 5 microns. When that starts producing science, that will have more people clamoring for higher and higher spatial resolution. I could just imagine how much fun it's going to be taking that on a disk in torus at 3 microns and starting to see where the water lines are coming from exactly. Yeah, that'll be a lot of fun.
For young people.
I might live for that.
Question? Okay, so we can end here. Matt, thank you very much for coming here and giving us this nice talk. Well, this is the end.
I caught it.